Welcome everybody to the Mechanical Engineering Department seminar. This is our second seminar on the mechanical engineering for portability. And I'm extremely excited to introduce Professor Hong Yao from Georgia Tech, who 10 years ago graduated from his PhD from the University of Washington. So this is a wonderful 10-year reunion for him. So thank you all for coming to the party. Since his time at UW, I'll let Hong introduce his background, but he's definitely one of our star alum from our department. He's had quite a productive career as his own faculty. He has published in Nature Communications, PNAS, Advanced Materials, number of high Nature materials. He has quite a energetic and active research group and has done fantastic in being recognized in his work. Some of the awards that he's received has been from the Biomedical Engineering Society, an Innovation and Career Development Award. He has had advising back to the KAIST Institute in Korea. And I think probably the best award he ever got was his poster award when he was a PhD student here at UW from the ASME IMECI conference. So I think that's probably the most cherished award that he ever got, was the one he got while he was here.
Exactly.
But I'll for everyone who's in attendance, we'll have a Q&A after the presentation, but feel free to use the chat feature or the Q&A while presenting for any questions, and we'll answer those at the end. But without further ado, I'll let Professor Yao present his work.
Okay, let me start sharing. All right, I hope everyone can see the screen. Thanks for nice introduction, and it is my great pleasure to be here and share my research today. As he introduced, currently I'm at Georgia Tech. I'm an assistant professor in mechanical engineering and biomedical engineering. And I'm the founding director of the IEN Center for Human-Centric Interfaces and Engineering. And today I want to share something that I'm doing regarding smart and connected soft bioelectronics. But before jumping into research, I want to briefly introduce and share my academic journey. As I introduced, I started my graduate career over there in Seattle, 2006. And I got my PhD under the guidance from Dr. Chung in 2011. I missed that time. I was so young and looks happy. After that, I wanted to, explore different places. So I sort of drove across multiple states, and I went to Midwest, state of Illinois, over there, where I did my postdoctoral fellowship under the guidance from Dr. John Rogers. So I did study material science and bioengineering at University of Illinois Urbana-Champaign. Afterward, I got a job, finally, real job. So I moved again. I drove to East Coast, now state of Virginia. And I started my academic career, independent career, as an assistant professor at VCU Medicine and Engineering in 2014. So I stayed there for 3 years. And afterward, again, I wanted to explore a new place. So I drove down to southeast state of Georgia. And so I moved to Georgia Tech in 2017. So now I'm in mechanical engineering and biomedical engineering. And thankfully, I got tenure and I'll be promoted to associate professor in August. So I feel very lucky for that. So this is my academic journey, and people ask me when I share this, what's next? It's a very good question. And so when I look at this map again, then I was always fascinated by Hawaii and Alaska. It was a great place. So I was thinking about that, and all of a sudden, I have a family and I have a wife who doesn't want to move anymore. So happy family from happy wife. So I'm thinking I'm gonna stay here for a while as of now. Okay. From this journey, I learned something. I learned a lesson, and hopefully I want to share something that I learned with graduate students who are here. From this journey and from these multiple cities and schools where I live and attended, I learned that, and I want to share this with you. Do not be afraid of change. That's initially I was really, afraid of moving and changing places and meeting new people. But these opportunities where I met different people with different cultures, backgrounds, really helped me to learn something, and I made new friends, new connections, and eventually, I believe that it's leading me to a new beginning, and it will lead you to a new beginning that you never thought of. Okay, that's a little bit about myself so far. And from now, I'm going to talk about something that I'm doing here at Tech. This is my research group at Georgia Tech. And currently, I have 8 postdocs, 19 graduate students, and about 20 undergrad researchers. So as a team, we are studying a few different aspects of mechanical engineering and biomedical engineering and electrical engineering. So we are looking at soft materials, flexible mechanics, electronic systems, machine learning, and system packaging. So based on the fundamental study, we are developing new biosensors and bioelectronics. I call it as soft material enabled electronics. So this picture summarizes some of the ongoing projects that I'm doing with grad students, postdocs, and others. So based on the fundamental study, we are developing wearable and implantable biosystems to advance human healthcare, health monitoring, disease diagnosis, therapeutics, and also for targeting persistent human-machine interfaces. But today, due to time limitation, I'm going to only focus on wearable bioelectronics. You may wonder the novelty or the uniqueness of soft electronics compared to the existing electronics. I believe that this picture captures the unique novel aspects of soft electronics. And now you see 2 different electronics, one on the finger, the other on the wrist. So I call the electronics on the wrist as rigid electronics because it's made of rigid sensors and rigid electronic components. And now we are using this soft wristband to wear this device on the skin. Compared to that, you can see completely different electronics on the finger. I call it as soft electronics. It has unique capabilities, including very small form factor. okay, because of the material that I used and the designs that I used. And this device offers better skin compatibility because I can use more skin compatible, biocompatible materials than the existing metals and plastics. And also this device offers better signals than the conventionals because of reduced and negligible motion artifacts. At the same time, the soft electronics is ultra thin, ultra light, and also deformable. So when it's mounted on the skin, it's giving negligible thermal and mechanical burden. So overall, by considering these factors, the soft electronics are offering long-term wearability so that users can wear this device not only for a few hours, but also for multiple days and multiple weeks. You may wonder how we can design such electronics. My group is studying multiple strategies to design and develop soft electronics, but I want to share a very simple case here. So this picture that's actually capturing my fingers, I'm holding a miniaturized rigid electronics that includes sensors and communication units. The question is, how can we make it thin, soft, and flexible? Again, there are many ways, but one simple way is to change materials. So now on the right-hand side, you are looking at the same electronics with different materials. So I replaced the existing rigid plastic substrate to soft polymer. And also I replaced the thick metal interconnects to mesh-typed nanomembrane interconnects. So by changing the materials and by reducing the thickness of the materials, once we reduce the thickness, then we can dramatically reduce the bending stiffness. So now the metal becomes flexible as shown at the bottom left. At the same time, instead of using linear designs, once you realize that mesh type meander features, then this nanomembrane metal can be integrated with soft polymers top and bottom to form a composite. So it can endure the applied strain by having out-of-plane buckling without losing or without having mechanical fracture, so that it can maintain the functionality. And by integrating the miniaturized chip components, we can maintain the functionality of this electronics as shown on the left, the conventional electronics. So based on this simple idea, we can build and develop various types of wearable systems, sensors, electronics. Today, I want to briefly share 3 examples of wearable soft electronics. One as a health monitor, number 1, number 2, as a machine interfacing system, and number 3 as a therapeutic system. So the first example is to use the wearable soft bioelectronics as a health monitor. So here we develop our own nanomanufacturing technologies to develop this system. And also based on flexible mechanics and soft materials, we develop a stretchable hybrid bioelectronics. So pretty much all the materials that I'm going to share today are at a very high level because of time limitation. So if you want to get the details, I encourage you to look at the published articles on this slide. Okay, we are trying to measure heart functions, heart activities. And this picture shows a typical arrangement of existing wearable medical devices. There's a patient on the bed. We use multiple metal sensors. They are mounted on the skin by using tapes. And there are separate components for powering and data acquisition. Obviously, she's using a laptop over there. This is a very typical setting that we use in 2021, still here, and exactly same setup that Emory University School of Medicine in Atlanta is using. And now, based on the system miniaturization and technology development, we are looking at miniaturized wearable systems shown over here. So for the bottom right photo, it's showing a wearable device that's an integrated heart monitoring system from one of the biggest companies, Medtronic. It's a single device platform. There's no wires. So it's a lot more convenient, and it can be wearable for multiple hours for sure. So everything looks good. However, the problem is that they didn't change the materials. So it's still based on rigid metal, rigid plastics, rigid packaging. So it's very heavy. So they had to use aggressive tape to mount this device to the skin and secure that contact. But more importantly, once you flip it over, when you look at the interface between the sensor and the skin, you see a bigger problem. Now the sensor is made of rigid metal, and our targeted skin is very soft. It has curvilinear features. That's why once you put this rigid sensor to the skin, then there's an air gap, which is causing electric impedance issues. So we are using this conductive gels made of sodium chloride. That's good, but now the problem is that this conductive gel is evaporating over time. And also when it's combined with this aggressive adhesive, then it can easily cause skin irritation, allergic reactions. And also because of evaporated gel, it can change the impedance over time, can degrade the signal quality. So to address those issues, my group developed a dry, gel-free, sensor-based biopatch, which is an all-in-one biopatch system shown over there, which has only 7 millimeters in terms of thickness, and the weight is less than 7 grams, including all the components and battery. And as you can see, that is very stretchy. The entire effective moduli is in the range of 20 kilopascals, like human skin. So once it's mounted on the skin, the users cannot feel anything. It's providing the ultimate comfort. Once you look at this device, it has multiple components. Okay, at the bottom, there's the nanomembrane electrode making direct contact to the skin to pick up heart signals. And on top of that, there's elastomer, strain decoupling chamber, and also the data processing wireless circuit. Okay. So to design such multi-component embedded electronics, we were using computational mechanics modeling to offer flexible and stretchable design so that we can avoid any unwanted mechanical fracture when it's mounted on the skin. So there are two major components, one nanomembrane sensor that makes the direct contact to the skin. So we wanted to make sure that the nanomembrane sensor is highly stretchable and flexible so that it can endure time dynamic changes of strain on the skin. And as you can see here, this nanomembrane sensor can endure the applied strain up to 100% without any mechanical fracture. And on top of this sensor, there's the stretchable circuit. It has less strain compared to sensor because there's a strain decoupling chamber between the circuit and sensor. However, we wanted to make sure the fully functional device during the use. So as you can see, this circuit is fully bendable, and it can be bendable up to 180 degrees with the radius curvature is only 1.5 millimeters. And when you measure this wireless signal quality, it maintains the signal strength up to 20 meters with bending. At the same time, the system is also stretchable. So you can endure stretchability up to 20% or over 20%. And as you see at the bottom right, it's maintaining the signal quality with stretching as well. And how can we really fabricate such sensors and circuits? We are studying a few different manufacturing technologies. And recently, we are spending more time on printing-based methodologies using nanomaterials. So here, I'm going to show you a video clip. I hope you can see that. Right now, there's a little nozzle on top of that, and it's shooting silver nanoparticles. So it's basically drawing a nanomembrane sensor. Okay, it's called aerosol jet printing. The major advantage of this method is that it has really large working distance between the nozzle and substrate. And also, this printing method can handle multiple various types of inks, from metal to semiconductor, polymer, and even biological solutions. So it's covering the viscosity ranges from 1 to 10,000 centipoids. So based on this aerosol jet printing technique, we can print sensors and also circuit interconnects. Okay, so it can print not only 2D, but also 3D structures as well. So now we are stacking multiple materials like silver, polyimide, and graphene, copper, and so on. So this scanning electron micrograph, the cross-sectional view is capturing the multiple layers of printed nanomaterials that builds this circuit interconnects. And once we print everything, then we just simply integrate the key chip components on top of that. That finalizes the wireless circuit. So as an example for measuring electrocardiogram Hall activities, this circuit includes Bluetooth Low Energy microcontroller, and there's the little ceramic antenna, so that we can get the data by using a tablet or smartphone. And it has motion sensor, it has other analog to digital converter, and so on. Once we have this nano material-based electrode, then we can avoid using any gels or aggressive tapes, right? So on the right-hand side, once our sensor is ultra thin, then now it can follow the morphology of the skin, okay? So we don't need to use any conductive gel to cover the gap between sensor and the skin. So to understand better between the interface between sensor and the skin, we developed this analytical equation that includes sensors bending energy, skin's elastic energy, and adhesion. So based on this study, we got this graph that captures relationship between work of adhesion of the substrate embedding a sensor and the modulus. Excuse me. So the good thing is that we can maintain the low modulus in the range of kilopascals, but at the same time, we can have good adhesion to have conformal lamination of the sensor to the skin. So once we do that, then we can lower the skin electrode impedance down to tens of kilo ohms without using any gels, which is great because now we can measure signals without any gels. So these are photos of skin-mounted gel-free electrode. On the right-hand side, you see that nanomembrane sensor can follow the morphology of the skin, right? Okay, so based on this arrangement, now we can measure the electrocardiogram signals. So on the right-hand side, that's the skin-like electronics that we developed, single device platform mounted on the chest area. That's measuring electrocardiogram, showing the clear PQRST components that clinicians look at. When you compare that with conventional setting on the left-hand side, you see it's pretty similar, right? There's no major difference. That's good. Now, another, or I guess the bigger advantage of our device compared to the conventional settings, is that the ultra-thin skin-like electronics can minimize motion artifacts. So the graph at the bottom is capturing the electrocardiogram signals when a user is having significant motions like running and walking. Red curve is showing our device, okay? And black and blue curves are capturing the conventional electrophysiological monitors. So when a user is moving, then the interface between the conventional rigid metal and the skin having slipping issues and dissociation. And also any wires can cause a lot of motion signals affecting to the quality of ECG. Compared to that, our device is ultra thin and there's no gel. It's having pretty much same motions when our skin is moving. So that's why we can minimize those artifacts and maintain the signal quality, even a user is having different activities. So based on that, we recorded this video clip. So right now, I hope you can see that there's the user wearing our device is walking. And the embedded app is capturing the real-time continuous ECG signal on the top. In the middle, these are activity data based on acceleration and angular motion changes. At the bottom, we embedded algorithms that can calculate the heart rate activity, respiratory rate, and the motions that he's doing. Okay, so you can capture what a user is doing and whether this guy is having abnormal signals in real time wirelessly by using Bluetooth. If something happened like heart attack, things like that, then we can detect it and send necessary services like emergency medical service and so on. Obviously, that guy was acting, so you don't need to worry about that. Okay, that's how we can measure real-time continuous health data with people. Second example that I'm going to share is that now we can use wearable devices to target brain signals. And we are trying to utilize these signals for human-machine interfaces, let's say to control external devices like electric wheelchair and others. The motivation is the following. There are more than 3 million people in the United States who are relying on wheelchair. Many different issues causing such motion motor disability. And one of the main causes is coming from Parkinson's disease. Okay? And now Parkinson's disease is affecting more than 10 million people in the worldwide. So once you have this disease and people have issues to control their muscles, like hands and limbs and others, legs, so they are relying on this, electric wheelchair. But think about it, a person who's having these issues, hand tremors, then, they are having hard time to control an electric wheelchair based on conventional joystick. So to address that issue, many people in electrical engineering and neuroscience are looking at brain signal called EEG Electroencephalogram. So they are trying to use this brain signal that can be measured on the scalp area using sensors to enable machine interfaces. So they are trying to process that brain signals and send those signals to an external device like wheelchair shown over here. Now, the problem is that we have to wear this messy and ugly EEG cap to acquire high quality EEG signals. And underneath each sensor, we have to put the gel, as I told you earlier, to have nice contact between the sensor and the skin. So basically, after single use, you have to shampoo your hair, and there are a lot of wires that's causing many different issues and looks very ugly. So overall, it's problematic. So we ask ourselves that, can we develop a better system, which is a real world applicable, wireless, and unobtrusive? Okay? So I was thinking about it for like, I guess, multiple weeks. And, I saw this guy. I hope some of you recognize him. Is Lebron James, one of the best, I guess, one of the best, or similar to Michael Jordan, I guess, in terms of basketball abilities and, his career. When I look at him, obviously I love basketball and I'm a huge NBA fan. But when I look at him, I thought about something that I could do with something that he has, which is a headband. So I designed this fully portable wireless system that can use this headband to push the sensors to the skin through the hair. So there are dry electrodes that can slightly penetrate the hairs and make a direct contact to the skin. And then there's wireless electronics mounted on the back side of the neck. And we can have reference on the mastoid and others. Okay, it's fully portable system having no gels and no caps and things like that. And among different EEG signals that we can target, we are looking at steady state visual potential. These are the signals that are capturing natural responses to visual stimulation. So as shown in this cartoon, when a user is looking at multiple stimulation carriers, then we can measure the EEG signals on the scalp area. And then when you go through fast Fourier transform, then you can get this graph and basically recognize what kind of frequency signals that this user is looking at. So we can estimate the user's intention by analyzing the EEG signals. So based on that, we designed a little hardware setup shown over there. So there's this O-ring structure that has embedded flickering LEDs with different frequencies. So this user can just purely look at one of those LEDs, then we can capture the user's intention. And then based on that, we can control this wheelchair or others. And now when we do this, wheelchair control, machine control, it's very important to have nice data classification. So that's coming from high quality EEG data. So this picture shows our device compared to the conventional hair cap device and wireless device with gel electrode. When we measure EEG signals from the same setups, just different hardware, we can recognize that in terms of signal to noise ratio calculated by the target signals versus background noise, you can see at the bottom, our device gives the highest signal to noise ratio among others. That's because of reduced motion artifacts, as I told you earlier, and we don't have any hanging wires, so we can minimize that wire motion as well. And also at the same time, we are using low power systems, so we can minimize electromagnetic interference to the device. So that's why we can have this nice raw EEG signals. Then based on that, we can enhance the skin electrode contact further, so that now we can targeting to use our device not just for a few hours, but also for multiple days. So we are thinking to change this conventional dry electrode to something shown on the right, which has an array of flexible microneedles made of polymers. Okay, so once we have that, then it can slightly penetrate the outermost layer of the skin, sternum corneum, to enhance the skin electrical contact and also the stability. And this nice needle can be reusable more than multiple times to measure EEG. And the main advantage of this microneedle electrode is that it can maintain the impedance density over the course of multiple hours, shown as green bars. Now, when you compare that with conventional gel-based electrode, you see the conventional electrode has huge density degradation after 1 hour. So that's why you can use this dry microneedle electrode to maintain the signal quality. Then now, based on the system, we are gathering EEG data for example, here we have 5 different cases, 5 different inputs, alpha waves when eyes are closed, and there are 4 EEG signals from the flickering LEDs. And to classify the signal, we use the deep learning convolutional neural network that offers optimized signal features and outputs. So based on that, we got this nice accuracy, about 94% from 6 human subjects with 5 different input cases. And now we are getting about 99% with optimized machine learning and enhanced device condition. So this is a real example that I briefly showed you earlier. There's the LED stimuli structure with 4 different frequency LEDs, and we are gathering the data, the real-time data, with a smartphone or a tablet. And we are using these 5 different inputs as controls to make the wheelchair, powered wheelchair, move forward or stop or rotate different directions. So here, this video is showing someone who has now longer hair, is working with, any people basically. So this guy is wearing that device, and the top left, the graph is showing the real-time EEG that we are gathering when he's making some actions like eye close or looking at different frequencies, and then he's going to control this wheelchair based on his motions. Okay, so let's see how it works. So when he's looking at 11 hertz, the wheelchair was moving. He stopped when he closed his eyes. Right? Different frequency make the rotate motion. Now moving forward again. It's very slow because he's afraid of hitting the wall. That's why we intentionally slow everything down, but obviously we can control the speed and others as well. Okay, this is how we can do real-time control of this wheelchair by purely looking at the LED inputs. Okay. And now, as the third example of wearable electronics, here I'm going to share a case where we can use this wearable device along with virtual reality to target wearable therapeutics. Okay, so this study is trying to help people with convergence insufficiency. So basically, once you have this issue, then you are, when you look at text, then you see that doubled text. It's impacting more than 3 million people in the United States. And one of the disorders is strabismus. Shown in this video, this guy has involuntary motion. So he's having issues of convergence. Right? It can cause headache, attention disorders, and others. So to treat this disease, there are a few different ways in terms of therapy. Right? Currently, the well-known method is to use this physical apparatus at a doctor's office. Right? For kids and others, they go to a doctor's office and basically look at objects, right? Multiple objects with different distances from the eyes. Right? So they are training, the convergence and divergence by changing the directions of those objects. But the problem is that, they have to go to the office, right? And also, this is not a quantitative measure. Okay. So our idea is to utilize wearable electronics to help this vision therapy. So this is our setup that we developed. So we are using this wearable soft electronics. Okay? There are 2 components. One is stimuli electrode mounted around the eyes to pick up the eye motions. And there's an electronic circuit the backside of the neck to get the data and the send data to a receiver via Bluetooth. And you see that there's a virtual reality device. Actually, that's from one of my graduate students that he's using for his games. I sort of borrowed him from him to quickly use it for this study. So instead of doing gaming, here now we design these moving targets, right? So instead of having physical apparatus, now we can use this virtual reality so that you can change the design, the size of objects and the distances freely, right? Without making multiple systems. So here you see there are three cases: near object, intermediate object, and distance object. And as I told you, the nanomembrane skin-like electrode is mounted on the skin to pick up the eye motion. This eye motion signal is called Electro Oculography. Basically, it's measuring chorioretinal potentials. When you look at our eyes are basically polarized, like a magnet. So when you use a pair of electrode, then we can really measure the potential changes from the neutral location in the middle when eyeballs are moving either left and right or up and down. So it's a DC potential that we can measure, as you can see from that graph. Based on the moving angle, we can see the spike of amplitude along with the time domain. And on the right-hand side, this is an electrode mounted on the skin, and it's following the skin motion. So whether your eyes are moving or your skin's your face are moving, you can easily pick up those signals without having any detachment issues. And here we compare the performance of the skin-like electrode with conventional electrodes. So this subject is looking at multiple objects from the zero angle, neutral position, up to 40 degrees. And as you see from this graph, the amplitude is proportionally increases. Okay. The good thing is that if you look at the number, right, the skin-like electrode is having 13.3 microvolts per degree, which is really high potential that you can gather without having significant noise. So it can be really used to distinguish as small as 1 degree change of an eyeball. So based on the fact that we are looking at these EEG signals when a subject is doing convergence and divergence practice. So here, this is block string visual image from the VR. So a subject is wearing this, and he was looking at 3 different objects with different distances, right? And you see there are 3 different graphs showing the changes of EEG signals depending on his vergence motions. And we are following the conventional treatment setups that have 3 different objects, with different distances, like 40 centimeters, 60, and 400 centimeters away from the eyeballs. Then now each motion has about 1 degree change of the angles. So based on that, we designed a data classification algorithm to detect user's intention, okay? To see how well a user is responding to the program shown on the VR. So we are targeting 6 different things, like 3 targets in divergence and 3 targets in convergence. We're using ensemble classifier and multiple features based on this threshold consideration to get the confusion matrix shown at the bottom. So with 6 different subjects, with 6 different inputs, we got about 91% of accuracy to estimate how well users is responding to the input. So this is a real-time setup that is showing how the system works. Okay, so here's a user who's wearing, the nanomembrane electrode, and instead of talking, he will show us what he's looking at, whether near object, intermediate object, or far objects. Then on the right-hand side, top right, there are 2-channel raw EOG data shown. And at the bottom right, it has the embedded algorithm to show the real-time classification to see or to pick up what he's doing. So let's see how well it's working. Right, he's showing his intention. Bottom right is capturing based on the algorithm. Okay, that's the way that we can capture the user's efficacy by following the VR program. So here now we are playing with patients, real patients. So this is a real patient case here. He's having issues of convergence on the left eye, shown as red curve, right? It needs to be going down, but as you see that it's not going down, it's maintaining that angle because of involuntary motion of his eye, one of his eyes. So we work with this student who's having these convergence issues. And at the bottom left, you are seeing this real VR block string objects. So he's playing with this therapy for a while, and we got this accuracy data. On the first day, when he came in and played with this VR, he has accuracy of about 70-something%. That's something we can calculate based on the outputs, because we can see how well he's responding by looking at EOG data and classified data, right? In the second attempt, later, now he can have enhanced accuracy. He's following the program better than the first day. And then later, now he's getting about 90-something% of accuracy. So this is a way that we can really have qualitative follow-up of showing how well these patients can work with our therapeutic program. So based on these outcomes, now physicians or clinicians can change their programs depending on users' performance, and they can do something to make the system work better. So we are continuously working with more patients at Emory University School of Medicine here to further demonstrate our system's efficacy. All right, with that, I'd like to summarize my talk. Today, I briefly introduced some of the soft material use cases, flexible mechanics, manufacturing, and system integration technologies to develop smart and connected bioelectronics. And we are continuously working on advancing human health, human-machine interfaces, and wearable therapeutics. Thank you for your attention, and I'm very thankful for the research sponsors, and also I'll be very happy to answer any questions. Thank you.
Thank you very much, Dr. Yao. I can't hear everybody right now with the webinar feature, but I assume that they're all applauding you, which is great. Thank you. We have questions in the Q&A, but if you also would like to ask a question, please use the chat feature, or you can also raise your hand. I'd like to actually ask the first question to you. With the wearables, I know in past there's been issues with a person's skin tone, making, like, for example, a Fitbit is difficult to get a heart rate monitor on. I think with your designs that gets around some of those issues, but I'd be curious if there's been other things that you guys have discovered. For example, people who might perspire more than others, does that cause effects on the accuracy of the readings or how long a person can wear these?
Yeah, that's a very good question. I think skin tone, we haven't seen any big issues with that. We play with multiple subjects, and now we are working with Emory Cardiology to have a large population study, more than 100 subjects. But we do see the sweating issues depending on people. So as you mentioned, that some people sweat more than others. And obviously, depending on the substrate and devices that you have, it can cause that contact issue. So we do see that cases. So we're trying to have perforated membrane to target like multi-day long study. It's normally okay for having multiple hours, but sometimes people have issues with the contact issues when the time is over a day also. So we are making that arrangements depending on our target applications.
Excellent, great. So I'm start answering some of the questions here from the Q&A. The first one is Alex asks, have you explored any haptic applications for the conformal electronics? I think you've been developing sensors, but how about buzzers or feedback on that?
Very good question. Yes, I actually got new funding to study that, to have sensory feedback-based wearable system. So we are trying to help somebody who's losing their, nerve activities. So that we are trying to deliver that information based on pressure sensor, temperature sensor, and strain sensors. So we just started to work on, I guess, like 2 months ago. So hopefully you can get the data and share with you sometime next year.
Excellent. Another question is, what sensors and other electronic components have been made stretchable?
Okay, so it depends on devices. As I mentioned that today, I just show you 3 different cases where we have this wireless electronics with Bluetooth capability. For this specific case, as I briefly show you the circuit design, it has multiple circuit components to offer that active, data processing and Bluetooth wireless communication. So those components are not stretchable. However, the skin contact sensor and the circuit interconnects are all stretchable so that it can accommodate, the bending and stretching. Another case is that where we develop a totally stretchable system that has no chip components, because this sensor is using inductive coupling for communication. For that case, we don't have any hard chip components in the device. So entire device is stretchable. However, this guy doesn't have active communication. It's passive communication delivered by the external coil. So, depending on the target devices, we have a few different types of design concepts.
Great. The questions keep coming in, so I'll keep answering these for everybody here, or asking them. Another question again from Alex, who's asking, how do the heart rate monitors perform compared to the commercial ones by Garmin or Polar or Fitbit, for example, as well? Yeah,
I don't know whether you remember that one slide I shared that direct comparison between our device with other wearables, but that device is chest mounted, right? The conventional ECG settings. Garmin and other wrist wearable devices, I'm wearing one of those. It can measure ECG and others. However, you think about, the basic mechanism of measuring ECG, you have basically 2 different sensors. For example, this Apple Watch, you have to basically put your finger on it and make the other sensor connect to your wrist area. So you have to maintain that good connection. Otherwise, you're not getting good signal. So these wearable, wrist wearable devices are not really designed to give you continuous monitoring of ECG. So we are not really targeting that. So we are targeting more, continuous recording of ECG data 24/7. That's why we're targeting on the chest area. So compared to other, chest wearable devices, our device is better in terms of, removing motion artifacts. So in terms of outcomes, our device gives better quality because it has, better data by not losing those, ECG signals because of motions.
Thank you. The next question is from Ting Ting. She really liked your talk. Those are very exciting projects. The question she has is on what is the usability of the soft material that's used with these sensors.
Right.
Another part is there any estimate on the cost for the lifespan of such of these designs?
Good questions. As a mechanical engineer, cost is important, right? We are working on two different types of devices. One is disposable, the other is reusable. Disposable, we use nanomembrane sensors and others. We mount it on the skin and throw it away. Sensors only, not the circuits. Okay, so there are two parts. It can be detached separately. So for that case, I guess it's the case where we want to use that device for hospital settings to monitor someone 24/7, multiple days or multiple weeks, and they don't want to recycle the device because of infection and other cases. So we throw it away. But for a case where you only measure your ECG for 1 hour or 2 hours, then we can design. Basically, we can change the substrate. Okay, using I guess more film-based substrate versus elastomer-based substrate. So we have multiple choices to build a device. In terms of cost, good question. That's something I'm working on as well. We just started a company to do that. I have no exact number, but we are targeting to make sensor, nanomembrane sensor less than $1, and entire device less than $10. I believe it's possible based on screen printing and basically 100% printing-based manufacturing technologies.
Oh, congratulations! Good luck on the startup venture. It's a good time now.
Thank you.
You've got your tenure. You can explore bigger things too, which is great.
Hopefully, yes.
Then actually kind of leads into the next question from Melody. She says, "This is all very awesome. Thank you for the talk. How far are we before we could start seeing these devices being used in everyday applications? And what's the biggest challenge in implementing them?" I think she's trying to put a clock on your startup.
Yes, good question. I want to ask that question to my CEO. I don't know what plans that he has, but hopefully soon. We got multiple grants and funding, so we are making one of those devices. We are not targeting everything, obviously. We're targeting one specific device right now. Hopefully I want to scale up and target multiple things, but we'll see what happens. But in terms of, I guess, manufacturing principle itself, it can be easily scalable. It's a matter of how a company or other commercialization partner come in and take those responsibilities. But obviously, I'm not an expert in those commercialization and larger scale manufacturing. So I'm just doing my best, and hopefully I can have more people who can help me.
Great. Well, I look forward to wearing your stuff in the future.
Thank you.
I know I don't have any additional questions in the Q&A, but if you guys do have, you can also use the chat, or you can also raise your hand if you'd like to ask a question. Oh, is there one in the chat that came up? Let's see, the Q&A. Oh, there is one. Thank you. Okay. Stuart asks, I may have missed this point, but are there any considerations of using piezoelectrics for power longevity? I guess it's sort of like, harvesting power.
Right. Yeah, that's a good question. I haven't, received any projects for that. I wrote a couple of proposals, but didn't get it. So I didn't have a chance to really explore that. But one of my undergrad researchers is looking at that piezoelectric material-based energy harvesting. There's some issue to have, real world applicable device on the skin because we have good voltage inputs, but very small current. So that's something that we are trying to work on right now, but I don't have something, tangible outcomes to share right now.
And we actually have a Professor Jilan Wang from